All right. So remember what we're doing. We're in the log section now. Did you guys finish up 5.3 okay?
Yes.
5.3?
100% easy.
Is that good? Easy for you?
Last problem got you.
What's that?
Last problem got you.
Last problem got you?
Yeah.
All right, feel free to grab me after class. I mean, I do it now, but we just don't have time. Come grab me after class. Be glad to help with that. Did I answer your question earlier? Or did
Yeah, you did.
you good? Okay. So, all right, so let's keep going. So 5.4, so we got to get done today, tomorrow. It's a big, bad section. So first thing we're doing is how to change between the two languages, power language called exponential and log language, right? It's like saying 1 and uno, right? Same number, two different languages. So I want to say 2.3 is 3 to the x in another language. I want to say it in log talk. How do you say it in log talk? Base stays the base. Base stays the base. Other two switch. I'll say that a lot of times today and tomorrow, at least I'm planning to. So, all right, so what do I mean the base stays the base? Who's the base? Who's the base here? 3. 3 is the base because he's the bottom one. Base means bottom, you got something on you, right? So the base stays the base. So you write log. Log statements always have a number that's lower down. That's the base because that's what bases are, right? They're the bottom of something. Base of a table is the bottom of the table. So that's the base number right there. So the base stays the base, which means the lower down number will continue to be the lower down number. So the lower down number, no change there. Base stays the base, other two switch. What do you mean they switch? They just switch positions. Instead of 3 being to the x power, it switches 3 to the 2.3 and the x goes the other side. They just switch. That's it. That's all they want. They're just making sure you can translate between the languages right here in the beginning. All right, is that good? Now we're going out of the log. So now they're starting with a log like that, and they want us to cut it out. In other words, this is, I'm saying uno, and I want to go back to saying 1, right? I'm translating the other way. Whatever, same rule. When you lose a log, gain a log, either way, same thing. Base stays the base, other two switch. So who's the base?
9.
The 9, the base. The base will continue to be the base, meaning he'll have something on him. But instead of 9 to the 81, they'll switch, and it'll be 9 to the 2, and the 81 goes the other side. And we know that. 9 squared is 81. Well, the log is saying, that's what I was saying all along in my language. They're saying the same thing. Two different languages. Base stays the base, other two switch. All right, so log base 9 of 1 equals what? So now we're going to actually solve a log because they're not giving us all 3 parts. So notice there's 3 parts to any log statement. There's 3 parts. There's the base. There's what you would call the argument, the plug-in. It's like a function, and that's the holes in the toaster. Log is a function. All these things are functions. And this is like the holes in the toaster. That's where you plug in whatever. It's a log base 9 function. Plug in 1, and of course this is the answer. So there's 3 parts. The base, the plug-in, the answer. So on the last problem, they gave us all 3 parts. The base, the plug-in, the answer, and so they just wanted us to rewrite it. It was just a rewrite question. We didn't really solve anything on the last one. We just rewrote it in another language, said the same truth in another language. But now they want us to actually solve. They want us to actually find the answer. They're not giving us the answer. They want us to find it. Well, how do you do that? Well, just pop an X over there. Just say, all right, you're X, just like naming a pet. You're Rover, right? You're just giving it a name. And now we just do the translation out of the log language because we don't naturally speak log talk. Let's go to regular. So how does that work? Well, you cross off the log word. When you lose the log word or gain a brand new log word, either way, in or out of the log language, the base stays the base, the other two switch. So the 9 will continue to be the low down number, and the other two will switch. Instead of 9 to the 1, it's 9 to the x, and the 1 goes over there.
So x would be 0.
So x is 0. By clear observation. X is 0, right? What to the, anything to the 0 power is 1, huh?
Can you just do that without...
Absolutely. If you don't need to write this, you can just see it, feel free. Yeah. 9 to the is 1. Everybody good with that? Anything to 0 power is 1? Why is that? Is that a weird rule?
No.
Yes, no? Maybe so?
Can you explain it?
But the 9 to the 1 is...
If it doesn't feel like they're just making it up sometimes?
Yeah.
Like, I mean, why is it 9 to the 0, 0? Or something else? Why is it
Oh,
1?
it's not because you're not going up a power, but it's still 9. So it's just one.
I'll show you two ways real quick. I probably shouldn't have even gone here. We don't have much time for this. But I just like the purity of math. I like to show how it's just going by what's true. And that one really doesn't seem true, does it? That one just feels like, no way, they're just making that up. 9 to the 0 is 1? Why would it be 1? Well, actually, just look at what you already know and you'll see it's got to be true. What is 9 squared? 81. What is 9 to the first? 9. So follow the yellow brick road, follow the pattern. 9 to the third, if you want to do another one, is 729. So what's happening from jump to jump to jump?
Multiplying by 9.
It's dividing by 9, or yeah, going down, it's dividing by 9, right? You're dividing by 9 every time, dividing by 9. So 9 divided by 9, it's got to be 1, doesn't it? That's true of any, pick like 2 to the fourth, 16, right? 2 to the third, 8. 2 to the second, 4. 2 to the first, 2. So 2 to the 0, next one, what are they doing every time? Dividing by 2, huh? So it's got to be 1, doesn't it? So it's got to be true. Let's just do it. There's another way, but good enough. There we go. So it is. Anything 0 power is 1. It's just true. They're not making it up. It's just true. All right. Okay. So log base half at 32. So what do? You just pop an x on the other side, huh? So let me let you take it from there. So you know what to do, right? Cross off the log word. Base stays the base. Other two switch. Base is a half. That one's a little tricky. I'd be impressed if you come up with it. Don't say that loud. Give everybody a chance. So we put an x on the other side because they want the answer. Cross off the log. Base stays the base. The half is the base, right? That's the base. The other two switch, which means these guys switch. Instead of half to, it looks like half to the 32 power. It's made to look that way. But they switch when you lose the log word, right? So a half to the x equals 32. Good so far? Base stays base. Other two switch. Now, and really it should be that way. That way you don't have to, but really that means the whole half to the x. I'm fine if you don't write that, but technically it's supposed to be there. Because if I don't put it, it really means only the 1 is to the x. We know what we mean, so I'm not real picky. But anyway, that's technically right. Okay, so now what power on that half? How can you raise half to some power and get 32?
It has to be even, right? It has to be negative.
First thing is you have to flip it, don't you? You got to make it 2. So we know this power is going to be negative. How you doing it? Think and see. Remember I promised? You'd have to think negative powers backwards. Here we are.
And it has to be even, right?
And just I would just take my calculator out. You don't have to memorize this stuff, right? You just got 2 times 2 times 2. You'll find that it's 5 of them. 2 times itself 5 times is 32. So then what does this power have to be here? Has to be negative 5, doesn't it? Because the negative flips it, makes it a regular 2, and then 2 to the 5th is 32. So x is negative 5. Do a few of you get that? It's good work if you get that. Good. Is that making sense then? So whenever you see a fraction, just think about the flip thing. You know your power's got to be negative to flip it. And then just however many 2's make 32. Multiply together. Are making us think powers backwards. They're not giving us the power. We're finding the power. We're thinking powers backwards. Because that's what logs are, inverse exponentials. Okay, try that one. Put an x over there on the right side. Lose the log. Base stays the base. Other two switch. And see if you can figure out the power needed. Put an x over there, lose the log, base stays the base, the other two switch. Instead of root 2 to the 4th, it's made to look that way, it's root 2 to the x equals 4. You good to there? So now think about how many root 2's, right? Because the power is a repeat symbol, isn't it? It's repeatedly multiplying. So just ask yourself, how many root 2's do I need to make a 4? Yeah. Root 2 is plane 2. 2 of them make a plane 2, huh? Because that's root 4, which is 2. 2 more make another plane 2, so yeah, you need 4 of them. So x is 4. Is that good? Making sense? We're just thinking powers backwards, aren't we? That's what logs are. Inverse exponential. Math Excel seems to be doing real well now. Just had a little trouble. All right, h of x. I'm just going to make that y, because I think it's just easier to do it that way. Okay. So, what is the they want domain? What else do they want? So yeah, so I haven't talked to you about domain yet. Let me tell you about domain. Domain inside of a log. So remember, like I told you, this is the plug-in, right? right there. That's the holes of the, well, it's the whole thing here. That's the holes of the toaster. That's the, it's like f of x. That's the, f of x, except it's log base 7 of whatever. Does that make sense, what I'm saying there? A log is a function. All these things are functions. Trig, sine, cosine, tangent, those are all functions. E to a power, that's a function. 2 to the x, that's a function. All these things are functions, which means you plug stuff in, you get stuff out. So log base 7 is a type of machine. It's a function, like a toaster. You put stuff into it, you get stuff out of it. So what does that mean? Well, here's the input slot. The domain, remember domain means what you're allowed to plug in. Right? Domain is what you're allowed to plug in. Remember, what do we have so far? We have the square root. Inside of a square root, we always say, well, what can you plug into square root? Well, it's got to be greater than or equal to 0. Can't be negative. What we have denominators. What do we have for that? That cannot be 0. Whenever you plug into a denominator, it cannot be 0. Right? So those are the two conditions we have so far for domain. We're going to add one now for logs. And that is the inside of a log must be greater than 0, not equal to 0, and not negative. You can't put a negative in a log or even a 0 in a log. You can try to calculate or say error. Take the log of a negative number or log of 0. It'll be error. You can't do it. So domain is very similar to square root, except you can't have the equals. So, right, like the inside of a square root has to be greater than or equal to 0. The inside of a log, just strictly greater than 0. Good? So that's the domain. So that's the answer to this one. All positive real numbers. Just positive numbers on that one. All right. So we have the natural log of 1 over x plus a. So what are we supposed to do? So what I did, natural log is just a certain kind of log. We'll get to it. It just means log base e, but whatever. We don't care right now. It's just another log. It's just a certain kind of log, but whatever. It's a log. And so what did we learn about the inside of a log? The inside of a log has to always be greater than 0, right? So put that on your 3 by 5 card. So that means the whole 1 over x plus 8 thing has to be greater than 0. Doesn't it? Does that make sense? 1 over x plus 8 has to be greater than 0. Okay, now, what does that mean about x? What values of x will make that greater than 0? What do you guys think? How do you, can you just say the denominator has to be greater than 0? You can, huh? Right, because as long as the bottom is positive, greater than 0, positive. The top's already positive, positive over positive will be positive. Is that good? Am I going too quick on that? Does that make sense? Now, it'd be a different story if we had fancy stuff in the top as well. But, yeah, if you're just looking at a fraction, the top is 1, and you're wondering, how do I make this guy? It's like me asking you, hey, how do you make that fraction be positive only? That's what greater than 0 means, huh? Positive only. Well, as long as the bottom is positive, because the top already is positive 1. So as long as the bottom is positive, as long as the x plus 8 is greater than 0, positive. So then that's easy to solve. X is greater than negative 8. That's our answer.
It's negative already, so then it's going to be x is positive 8 in the answer?
Yeah. So yeah, good question. Like if you have negative 1 over x plus 8, is that what you're kind of saying?
No, it's 1 over x. On mine, it's
What-
x minus 7.
Okay, yeah, let me do that one. So if you have 1 over x minus 7, it's got to be greater than 0. Then you would just take just that and say you got to be greater than 0, so x is going to be greater than 7. On that. Just solve the denominator greater than 0. Good? On that? So you're doing that homework problem right now? Did they want interval notation on that last one, or did they just want...
Yeah.
They did? They actually want an interval? Yeah. So on this one then, you would say negative 8 to infinity, huh? On that one. Anyway, you guys got your calculator? Natural log of 16 over 7. So hit the button, see if you can get that. I'll put the answer once I can find the buttons. Natural log 16 divided by 7. Should be, they want round to 3 places. So 0.8266. So third place, look one to the right, 0.827.
Yeah.
You guys getting that okay on your calculator?
Wait, no, what do we do?
Natural log of 16/7 there. Yeah, feel free to compare with those around you. If you have any troubles, you still can't get it, come up after class, be glad to help you. Calculator stuff's 10 seconds. Be able to help you with that. Just do that right here in class, right after. Good, keep moving along. I've been working with people in my office hours, and it reminded me that I should be a little more helpful with calculator stuff, because there's a couple little tricks that can get you. So, okay, so like this, if you're going to type this into your calculator, there's the difficulty with teaching calculus, because you all have a different calculator. If you have the newer, nicer kind that make it look like a fraction, versus like I have the old kind, like this. Here's what I mean by old kind. Mine puts it all on one level like this. You know, it doesn't actually make it vertical. I have an older one. So if you have an older one, you have to be more careful. Here's what you have to do. You have to put parentheses around the numerator. So if it's all on one line, like my old calculator, then you have to put it all on one line. I'm sorry, that didn't make any sense. You have to put parentheses around the numerator and the denominator. Now, if it shows it like this, vertical, you have a newer one, then great, just type it in. You don't need parentheses or anything. It's all good. It knows exactly. But if it's all in one line, you have to put parentheses around the numerator and denominator. Why? Because otherwise it'll only divide. If you just write it like this without any parentheses, I think if I tell you why, it'll stick with your mind better. If you just write it with no parentheses, the calculator thinks to only divide those middle two. It doesn't realize you want the whole thing divided by the whole thing. It doesn't get that. So you have to put if it's all in one line. If it's vertical, it knows exactly what you mean. So anyway, I better give an answer here. Well, anybody got it? You guys already got it while I was doing all that talking?
6.30.
6.30. I just need one more. It's like a cliffhanger here, Barbara. What is it, 2?
2.
Okay, 6.302.
Next one is
Anybody else getting that? No. Okay, let me try real quick. Natural log 28
I
plus.
don't know, maybe I input it wrong.
Yeah, it's easy to hit the wrong button or do something tiny. Whoops, I just messed up
I
too.
just didn't enter everything.
Natural log 28 plus natural log 14.
Oh, maybe yeah, I should have to use.
Wait a minute, I keep messing up. Natural log 28.
Do set of parentheses.
Mine does these parentheses automatically all the time. It sort of bugs me. Yeah, there's a lot of parentheses. You gotta be careful with all your parentheses.
And 14 parentheses, parentheses.
Okay, here I got 2.3025. That 2 rounds to 2.303. 2.303. Guys, getting that? There's a lot of. Got to be careful with your. Mine does these like automatic little parentheses, like that. So I end up with like a lot of parentheses.
Oh yeah, I had to do the set of parentheses.
Yeah, parentheses within parentheses. So because mine's all in one level.
Yeah,
So
6.30.
all right. So make sure you can get that answer. 2.303. If you can't, come up after class. 10 seconds. Be able to help you with that. Isn't that good? All those parentheses. Actually, just kind of warming up. All right. So they're giving me y equals 5 to the x. And then they're saying, hey, the inverse function of that is log base 5 of x. So here we get our first clue that logs are inverses of exponentials. That's indeed exactly what they are. Logs and exponentials are inverse functions from each other. Okay, so what does that mean? What they want us to do is graph both these. Well, we already talked about last 2 days how to graph things like 5 to the x, right? How to graph exponentials. That was last night's homework and everything. So how do you graph an exponential? What do you do? Remember I wrote out a times b to the x plus c. And the c is the what? The horizontal asymptote, which this is plus 0. This has no horizontal asymptote. So remember, what's it called? The exponential graphs always have a horizontal dotted line. Guess what logs are always going to have if they're the inverse? If exponentials always have a flat dotted line, then logs are always going to have a vertical dotted line. They are. vertical asymptote line, yeah. So we'll get to that in a minute. But first off, so flat dotted line because there's no number out here, 0. The C is 0. That's the horizontal asymptote, okay? And there's no A in the front, which is really 1 times. Remember, the A is the jump. Positive 1, that means up 1 from the flat dotted line. Remember how we learned to graph that last 2 days? And then 5 to the x. Remember, the base doesn't matter much. It's just they go up to the right. They rocket up to the right. They come down for a landing to the left. Unless there's negative somewhere flipping things. That's the general look of an exponential. Okay, so that, I should actually probably make that the same color as I'm... See, the colors will matter a little bit here. So I'll make it black because I made this guy black. So that's 5 to the x. Okay, now on the same axis system, they want me to graph the log. Well, all I need to know is the log here is the inverse function. And remember, the picture of an inverse function is always the reflection across the dotted line. That's why there's the diagonal. I shouldn't call it the diagonal line. Right? So if you take that kind of, whatever you want to call that thing, that exponential graph, and you flip it across the diagonal line, can you see what it's going to do? It's going to come to that other side, and it's going to go like this. Can you picture that? So that's going to be log base 5x. I just flipped it across the diagonal line. It's like a butterfly kind of thing, right? That's what now, I didn't give you any reasons for that. We're not there yet. We're going to in just a minute. But for now, I just said, hey, you know how to graph exponentials. We learned that last 2 days. And this is the inverse, so flip it across the diagonal line. That must be the picture. So which one's that? Yeah, it looks like A, huh? A it is. Good so far? Now, we don't know why the log thing does that. We haven't got the rules yet. But so far, it's inverse. Okay, flip it across the diagonal line. Inverse functions always flip across the diagonal line, don't they? Everything else, I'm going to give you the basic one. And then, you can do all that you know to do already with flips and movements and all that. All right, so what's the basic? Let me just give you the basic. Log base b of x. Here, let me go. X plus c. Let me put it in there. Yeah, that'll be good. Okay, what is the general look of that? Well... The plus C means a vertical. Remember, they have a vertical asymptote line at negative C. I'll just say at negative C. Because remember, x is always opposite, and anything that's in the little x world is always opposite. So plus C means negative C. So that means go back here to negative C. And at negative C, put a vertical asymptote line. And then, other than that, the log graph basically takes a dive at that vertical, right? It never touches the vertical, takes a dive, and then goes up to the right. But notice it does it concave down. You want to start thinking about concavity now? Concavity is like the turn of a bowl. So if I take a bowl and I turn it upside down, that's concave down. Concave down. That's like what our log is. See how it's like a bowl turned down, kind of? But exponentials, let's go back a page. Exponentials are a bowl turned up, aren't they? Because they grow fast. Concave up, bowl turned up. So you want to start paying attention to that in graphs. It's a big deal in calculus. It has to do with the second derivative, positive, negative. You can figure out concavity. So start thinking about concavity. Bowl turned up. Things that go up fast, like exponentials, are bowls turned up, concave up. Things that go up slow. See, that log still goes up forever. He will. He'll never stop going up, but he's sure not doing it very fast. He's a slow growth. Slow growth. Concave down. All logarithms, because they're the inverse of an exponential. So, yeah. So make sure when you do your log graph, it's concave down like that. All right, so there's the general one, and then other than that, you got the flips and all the normal things. But that's what you want to put in your 3x5 card for the basic picture of the general log graph. Vertical asymptote, exponentials have horizontal asymptote. It's all about that C, it's opposite. Okay, anyway, so what have they done on this one? Looking at this one, x equals 1, so that means log base b of x plus 1. No, minus 1, huh? minus 1. Good so far? Remember, it's the opposite of whatever that number is your c. Good. The b, you can tell they're all log base 3. So I'll just stick a 3 in there. It's clearly 3. So log base 3, they're all log base 3. So now, but not only that, normally that would put it here. That would put it on the right side of the dot. That's where they normally are. But this one's been flipped to the left. So it's got a horizontal flip, huh? So what will do that?
A negative in front of the log.
Well, remember, a negative in front of something is a y effector, isn't it? And for any function. That would make it flip down. That would make it go like this. Go down instead of up. So that's not what's been done. It's been flipped sideways, a horizontal flip. So that means that x has been made to be negative x, huh? Let me fix that. So that x is negative x. Y'all with me on that? Now, this one's tricky. Remember, back when we first learned about all these flips and movements and stuff, that if you have two things in the same direction, not just two things, a flip and a movement in the same direction, that can be pretty tricky because the order matters. Whether you flip first or move first then flip first, it kind of makes things kind of jump around ways we're not expecting. You got to be a little careful. And I usually suggest making a table at that point because it's pretty tricky to track with it all. Do you remember what I'm talking about? So if you have both a flip and a movement vertically, or if you have both a flip and a movement sideways, that's pretty tricky. I would make a table. Well, we have both a sideways flip and a sideways movement here, don't we? So that could actually be +1 is my point. I'm not sure because of a whole story about which one was done first. So I'm not sure which one. The only way I could be sure would be to make a little table. Let me show you how easy it is, though, to make the table. Probably only 1 point. I'm wondering, is it minus x plus 1, or is it minus x, log base 3, of minus x plus 1 or minus x minus 1? I know it's a minus on the x, because the graph has been flipped sideways. And I know it's either a +1 or a -1. Normally that would be -1, because I told you logs are opposite. But maybe the flip happened afterwards or something weird, so I'm not sure. How do you know? Just try plugging in a point. Look right here. How about 0, 0? 0, 0 is supposed to be on the graph. If I put 0 in for x, what am I going to get? If I put 0 into this one, I'm going to get log base 3 of -1. Is that okay? That's not it. How do I know? I know I just said it, so it's probably not sunk much in your mind yet. Remember what you cannot put into a log?
Negative.
Negatives or 0. That if you do that in your calculator, now I know you might not be able to do log 3. I'll show you later how to do that. But let me just tell you now, it'd say error. If I will show you maybe tomorrow how to do logs of funny bases on your calculator. And when you do, it'll say no. It'll go error. It won't say no. It'll say error. So that's not allowed. So that's clearly not the right one. Because whereas you do 0 in the other one, you get log base 3 of plain 1. And that indeed is 0. That's true. That's right. So this is the one. Log base 3 of minus x plus 1. So where's that one? Yeah, do you see it's a? They just turned it around. Minus x plus 1 is the same as 1 minus x. That's it right there. That's not easy, is it? Do you see all that? Makes sense on that? Yeah, none of the other ones are right. Oh, by the way, let me suggest, you might think, no, none of the others are right. By the way, this one minus 1 here, notice that's a y minus 1. He's not in the parentheses. That's a down 1, isn't it? That's not it. Everybody see this one's not in the parentheses. So that's a y effector, huh? That's not plugged into the toaster, right? It's a big difference. Big difference whether you're in the parentheses or not. If you're in the parentheses, you're plugged into the toaster, you're an X kind of thing. That minus 1 is outside the parentheses. So it's really out, only the X is plugged into the log, the minus 1 is outside. So that's up, down. Anyway, that's not our choice. It's A. Is that good? Does that make sense? Maybe I should show you at this point how to do. Yeah, you guys have your calculators? On your calculator, you have 2 buttons. You have a log base 10 and a natural log, which means base E. We'll get into that later. Anyway, so you could easily do like log base 10 of 3. You guys have your calculator? Just hit log of 3. That button that just says plain log that doesn't say anything, it means log base 10. So if you just hit log of 3, that'll be log base 10. Here, let me do it too. And log 3. So I'm getting 0.477.
Yep.
So, right? Everybody good with that? Now, the question I'm asking is, well, how do you do something like log base 3 of, I don't know, 2 or whatever? Like, how do you do log of another base other than 10? Some of the real fancy calculators can enter their own base, and if you got that, great, go ahead. But most of our calculators don't. So how do you do log of a base other than 10? You make it 2 logs. Log base 2 over log base 3. I don't have time to give a mathematical proof for why that's true. Maybe later, probably never. But come to offstairs, be glad to go over that with you. But anyway, let's hit the buttons. 0.6309, whatever. You guys get that? What's that?
Do you need to put parentheses?
No, there's just one thing on the top. Yeah, good question. There's only one thing on the top, one thing on the bottom. So no parentheses needed. Yeah, really good question. It's only when there's more than one thing in the top. Or like 2 things, yeah. Or multiplying. It doesn't matter, adding, multiplying, whatever. If you have 2 different things on the top or bottom, then you need to parenthesize. Right, that's just, unless you have the calculators that show the nice vertical. Right, that's a good question, Erica. Is everybody tracking with that? So yeah, so you guys able to get this? So my point in this is I know I could be saying this and it not making any sense. Let me be real clear. Your calculator will do log base 10 naturally, right? Just the normal log 3 means base 10. Every log really has a base. There's no such thing as a log without a base. So when you just do the normal log word, that means base 10. They call that the common log, meaning it's just the one that's used in real life, real world applications of logs most commonly. So they just, after a while, like anything else, they just said, hey, if I don't write the base, I mean 10. That just happened like any other field pretty naturally. So the normal log word on your calculator is base 10. So if they ask you to do log base 10, just hit the log button. But if they ask you for any other base other than 10, you got to make it 2 logs. Everybody with me on that? And a lot of times I have students, they'll get the order mixed up. So let me help this way. The higher one goes high, the lower one goes low. Notice. That order matters, right? The low one went low, the high log went high. So let's do one more. How would you do log base 10 of 20? Just hit, yeah, since it's log base 10, that just means log 20. So hit the button. You don't need 2 logs, in other words. You guys tracking with me? If it's log base 10, you don't need 2 logs. That's what the button naturally does, right? So 1.301, blah, blah, blah. But what if I asked you log base 9 of 20? You got to do 2 logs if it's anything other than base 10, right? So the high goes high, the low goes low, and you get whatever you get. Log 20 divided by log 9, which is 1.363. We good on that? Okay, now we're able to go back to these little questions I asked you. Now, try this one on your calculator. Now you can do log, I mean, I told you it was no, but now you can see it for yourself. How would you do log base 3 of -1? You would start, the high goes high, the low, because it's not a base 10, so we got to do 2 logs, right? The high goes high. As soon as you try the high, and go log -1, try it, calculator will go error. So then you know it's a no. And the other one, try the other one. Why is this 0? Let the high go high, the low go low. So that should be log 1 over log 3, right? Whenever the base is not 10, you got to do 2 logs. And you get 0, because the top is 0, it's 0. Everybody good? That's why it's 0, 0. You all good with that? So you can get your own log values now, make tables whenever you need to. All right, good. Let's do that. I don't have time. We got a whole section tomorrow of inverse ones where they make you do the exponential, the log, invert it, domain and range of both. Big, long problems. We need to get to those. So pretty much devote tomorrow to that. So, all right, let's do it. Let's work backwards. So it's some kind of a log. Log base b of x plus c kind of thing, you know. Look at the bases. The bases are all 3, so I'll just fill that in right now. All right, what's the c? That's the vertical, but it's the opposite because it's by x. So it'll be -1 in there because this is +1, so it'll be the opposite. It'll be -1. Log base 3 of x minus 1. Good so far. This one's going to the right. That's the normal thing. No flips. It's going up to the right. Up to the right. That's what exponential normally does. That's what log normally does. That's pretty much the normal state of almost all the graphs. Up to the right. So that should just be it right there, huh? log base 3. Is it not there?
Isn't it A?
Oh, it's A, yeah. I'm just spacing out. Yeah, thank you. Alexandria saw it. Yes. Good? There it is. Why is it not D?
The one's not negative.
Not in the parentheses. So what would that one do? In D?
That would affect X.
That'd be a Y. That'd be up, down. Because that's not in X's world. Right? You know what I mean? This one's in X's world. He got in there with X's world. So he has a right-left effect, opposite. He goes right. He moved the graph to the right. That's why that happened, huh? But this one is outside of X's world. He's a Y effect. He'd move the whole graph down one, wouldn't he? Different.
I'm calling it 30 seconds.
All right. I feel like you're the referee here, man. All right. So natural log of x plus 6. Let's do what we can. Natural log of x plus. Now, we haven't talked much about natural log. It just means log with a base e. You can just remember every log really has a base. So I'll stick it in there. You don't need to, but I'm just letting you know. In a minute, well, maybe not a minute. No, not today. In a minute, we're out here. But tomorrow, we will need to do some stuff with that. But for now, I'll just say it's just a special log. It's with that special number e, like that. All right. So what do they want me to do? Domain. So what's the domain? Can we graph this? What's it going to look like? What's that plus 6 going to do?
All the way to the right.
Left 6. Because remember, opposite.
Oh yeah, I already made it.
Negative 6, and then it's going to go like this. So what's his domain?
Infinity. After that.
Negative 6 to infinity, huh? Right, because this is the domain right here. All the places the graph exists. And we got the graph right there. I got that. What's the vertical? X is negative 6. That's the vertical. Hits the x-axis at negative 6. And that's all we have time for today.